I hope it works now, right? Yeah, you know what? We are inventing all the time. This time we have a new way of demonstrating the slideshows, distant slideshows, saying that I'm sitting somewhere else and the guys in the lab are doing their job. So I'm trying to basically discuss my part when they are doing their own part, and then we marry all that in one Twitch stream. So hopefully next time it'll be better. So today we're talking about this wet-sieving process, and I want you guys to see the stepwise approach with wet-sieving. All right, so it works this way. So we have to check this as a separate slideshow. Be possible to show one by one. Somehow it doesn't work. It should work for presentation. So we'll be working with this mode of showing the slides. So anyway, we've already seen this flow chart. We'll get back to it. So wet sieving. Wet sieving is a process that can be done using two ways. It's either automated way with a special automated screening device, or manual. And there are advantages and disadvantages of both approaches. So I tried to list them all in this slide. So first thing first, I would like to tell you that yes, there are many labs that are using automated wet sieving and just any sieving, but for our own research, we have skipped the automated sieving because of different reasons. Let's see why. First of all, though the automated wet sieving is faster, it's not clean. Manual is slower, but it's for sure 100% contamination free. First of all, due to control of the operator, because whatever is automated, you cannot control. You just can start and stop. And here you can literally control every particle under your hand. So manual is slower, but for sure it's the best control of any contamination, and plus it's less cleaning because those machines, they are full of different surfaces that have to be cleaned. Remember, we are talking about fine-grained particles of less than 40 microns sometimes. So you cannot see these particles, and the only way you can clean the labware is in an ultrasound. So we try and stay away of any automation on the stage of wet sieving. So also the manual approach is always less weight loss. It's also related to less vessels used for processing, and it's also many less spills, less decanting than if you use it automatically. So we would always go for manual in this case if we want to reduce the weight loss. Automated approach can lead to as much as 5% weight loss of the sample, and it's not good for balance calculations. So though it's the same labor cost, like it's the same guy working on or manual wet sieving, it's less care in a way if it works in automation, because any operator believes in automation more than in his own manual approach and in his own understanding of manual, and that's why there are many different mistakes to be made in this stage. So once again, we vote for manual wet sieving. Also, in terms of practicality, practical things, automated approach is also wear and tear of different sieves. Sieves are very costly somehow. These days, it's over €100 a sieve if you buy it in Europe, and each sieve, whenever it's broken, it's pretty much loss of your capital if you want to make it as a decent, project for your own, value. So then, what else is automated? Why is it used? Usually, it's used whenever there are chemical reagents, leftovers of processed chemicals that were used for previous, stages of processing, say processed products after cyanidation, processed product after flotation, these kind of chemicals can, first of all, leach the sample. And whenever you use automation, you cannot wash it properly. Sorry, when you use manual approach, you cannot wash it properly. But with automation, first of all, it gets washed. And also, you do not touch the substances that can be poisonous. With manual, also, you can work with very fine. And it's just that, it appears to be more handy. For our projects, we always use manual. Wet sieving, and that is what we will show you today, that Oleg will be doing manual wet sieving very precisely to show you how to do it. We want also to address the sieve. So important. It has got a separate slide. So cleaning of the sieves in an ultrasound between samples is essential, and we clean up to 1 day for the full set of sieves after each sample. And so that we would have to have 2 or 3 or 4 sets of sieves whenever we have one project, because anytime can come another project or another sample, so we can have no intersection between these 2 sets of sieves, and we can use it. So once we've finished wet sieving, we start hydroseparation on a subsequent different size fractions. So we start from the finest one, because we do not want to leach the fine grain size fraction by the coarser grain particles, because hydroseparation is so sensitive. So once we've finished wet sieving, we apply every size fraction to hydroseparation. So this is hydroseparator. CNT story behind it. It's 20 years now, I think, once the first hydroseparator was applied to, as I said in my first stage presentation, for recovery and concentration of precious metals, very fine grade precious metals. So for now, this approach is in many different areas of mineral research. So to say it works with best with less than 1 kilogram sample. I mean, it's the quickest way. First of all, it's representative, so you don't need to process as much as more than 100 kilograms, because 1 kilogram, if it's representative for the ore, it would always produce the same mineralogy. So 1 kilogram is optimum weight, though we led by the grades of desired elements that are within that mineralogy that we're looking for. So if we are talking about less than 1 ppm down to say 0.5 ppm, which is still enough to be 1 kilogram of the sample. But then if it's ppb quantities, milligrams per ton, it can be up to 3 kilograms a sample. So that's something else here. I'm sorry. Particle size 10 centimeter cube. I think it's left over from the other table. It doesn't relate to hydroseparation. So anyway, the particle size is a factor of, I don't know, where is it coming from this? Sorry, it comes from Spark 10, the table. Anyway, so anyway, just want to make sure that you guys understand that this the process that is totally computer controlled, all the regimes being preset, and the software controls it, so you can always go with whatever is preset in terms of regimes for different particles and different types of mineralogy. I mean, I will explain. It's just that because it's led by density, so there is a density range that you can use. So each density range corresponds to whatever specific regime you can set up and you can use. But it's also computer controlled, so you can actually program the device. It is used for solid water insoluble powdered samples to produce representative heavy mineral concentrates, we said, but it should be, those particles should be separate minerals. So basically every mineral whenever it's recovered by electric pulse disaggregation, is a separate grain, and it's got its own density. So we can apply that Stokes law in a carefully computer-controlled upward pulsating water stream to affect that density to separate these particles in a range between 3 to 20 grams per centimeter cubed. Once again, that's the mistake here. So we put here 3. So a grain size that is capable to be separated is less than half a millimeter and goes down below 45 microns. So basically, there is no other commercially available alternative for such grain size for separation of grains in this range below 45 microns. But the hydroseparator does it very well, even better than on a coarse size, because it's so sensitive. It's done practically no loss of mineral grains, and the concentration factors are up to 10,000 times, sometimes even more. So whatever you have in your sample will be concentrated as heavy minerals. It'll be concentrated by 10,000 times at least. So it has been applied successfully to different samples, having as low as 0.1 to 1 ppm. So from milligrams to grams per ton of the phase-forming elements of desired mineral. So it's totally patented device, 3 different patents. What else going to say? Here. So this hydroseparator is actually the process, as I said, that is led by the Stokes law inside the glass tube. Though you can use any other materials, but we always use glass because, first of all, glass is transparent. It's easy to clean. It's easy to bend because this glass tube has got this, as you can see, like a knee shape. So everything that is denser collects at the bottom of that glass tube at that knee, and everything that's lighter is led to the upper part of the glass separation tube, out of the tube with the flooding with a droplet of water. So any water is used, just tap water, same as with EPDs. So we all work with the same water. We can actually work with the same water that's left over from EPD, basically. So it's all the same water can be used. Because we have the water tank on the top that holds the whole process water, so we can pour that EPD water into the tank instead of the clean water. So it will all be the same range of particles. So it's another advantage of hydroseparation. But in all our projects, we just use the tap water. Later, we will show you the whole setup. Oleg and his assistant will be using other mode of Twitch to show you guys how to make wet sieving, how to make hydroseparation. It will be done in 15 minutes, so please wait. So the results of hydroseparation is usually 5 of the concentrate. So if you have 1 kilogram, you divide it on different fractions as a sample. So after EPD, you have that crushed, different size particles, sieved to different size fractions, and all of them will produce, or separate fractions will produce heavy mineral concentrates of the amount of 5 to 20 milligrams. So you can see here is the image of 2 hydroseparation concentrates. As you can see, they're very fine grained. Like this one is between 38 and 53 microns. Another one is from 53 to 106 microns. So the narrower the gap between size fractions, the better hydroseparation you will receive, because you can get rid of the size effect of different grains. So these hydroseparators are set up in different countries nowadays. It's over 100 laboratories using this device. It's either National Geological Service, universities, or companies around the world that are servicing mining companies. As I just said, that it's because they need the mineral separation by physical density. Any other method does it. Also, it's absolutely computer-controlled desktop equipment, which is easy to install and use and train any staff using it. It's for production of heavy mineral hydroseparation concentrates for research, with a particle range between 10 and 500 microns. And it's applied for mineral processing and sample preparation after EPD for successful mineral research. So what are actually the application areas where hydroseparation is so exceptional? This is one of the very important slides, I must say, because we have collected all different uses of the combined EPD and HS approach, which we call 3D laboratory, right? Which turns to become a 3D laboratory. Well, first of all, these are applications like to separate intact crystals or crystal fragments of diamond indicator minerals and microdiamonds. It's actually the application that has been already set up in many laboratories of different diamond producers. Like the latest one is in Rosa. We just set up there for hydroseparator, and like a few years ago we've set up their EPD, so they're now happily using both methods to concentrate indicator minerals and microdiamonds as a single shot, because otherwise they would have been using caustic leaching for this dissolution of the media down to microdiamonds. Now they can use the same sample for extraction of diamond indicator minerals and microdiamonds at the same time, because they all are in the range 3 to 4 grams per centimeter cubed, so it's within the same concentrate, so they can easily get that concentrate for their hand picking from any size fraction they need. Then the study of crystal morphology, mineralogy, and mineral chemistry of diamond indicator minerals, platinum group minerals, gold, base metals, and other useful constituents of different rock types containing low and very low concentrations. So there is no any other method that can happily recover, extract particles that has such a low concentrations in the sample. Like now, for example, we're working with sulfur mineralization, which is lower than half gram per ton. So it's very, very low grade, but we'll still be able to recover those sulfides of the sample. And this is our goal for this training. It will be done live with you online, be able to see all the operations. We have live stream every day, so you will be able to see all the steps. And next one is enhancing the chances of finding accessory minerals for their identification and characterization. It's to do with very precious minerals like platinum group minerals, gold, diamond, zircons, baryllite, and so on. These, like zircons and baryllite and other types of indicator minerals, are used for geochronology sometimes. They are very rare. It's like a few crystals in a subsequent size fraction, but we still recover them for age dating, for dating the rocks. Then it's for carrying out prospecting and technological mapping of on the face level from small samples to 1,000 grams. Like just recently, we have a stream of the same type of work we've done for prospectors, for guys who are prospecting the areas for gold, and we were able within 50 samples to find just 3 samples. I think it was 3, Oleg, right? So just from 3 samples, we found gold nuggets, very small grains. So quick, having just the concentrates and then pick particles from HS concentrates, which are very small. You know, the till sample can be hundreds of grams, and then you just separate particles, and then it's easy to hand pick them from the concentrate. So another application is to produce ultra clean separates of accessory minerals for any analytical purpose, such as mineral identification, isotopic studies, X-ray diffraction, etc., without using toxic chemicals and reactants which may leach or crush desired minerals. So it addresses to new mineral search, for example. It's whenever we have, well, basically, we always have new phases, new mineral phases in any sample when using EPD and HS approach, simply because otherwise they got, it's a single grain approach because you're working with single grain always. So if there is no other method, so if you extract all heavy minerals, definitely there will be new phases all the time, though. To make them new minerals, you need not just mineral identification, you need to basically make a lot of other research, like X-ray diffraction data, like physical properties. So this approach has been used successfully, for example, for discovery of 6 new platinum group minerals during last 10 years. And this is the only way to characterize grains of platinum group minerals from the host rock. All other platinum group minerals before invention of hydroseparation and electric pulse was discovered in placer deposits. And these 6 minerals were identified and extracted and basically analyzed from electric pulse and hydroseparation concentrates. And there will be many more mineral discoveries right now due to this application of these two technologies. Some say that basically application of these two technologies, discovery of the method of 3D technology, really is comparable to invention of electron probe, because it's such a big gap from what it was before and what is it now, because so many different objects now being found and characterized in mineralogy due to this method. So then the next one is to determine and identify accessory minerals, their grain size distribution, mineral associations, and other important information for economic application and extraction. Exactly the case when we try and implement 3D technology software to collect that data, such as grain size distribution, mineral associations, and other very valuable information for technology application, for best feasible mineral processing flow charts. This is very important. So next one is detect occurrence in possible secondary mineral deposits, such as product, mine tailings, industrial slags, etc. This is very widely used. We have these projects, consulting projects, quite often, because, you know, new resources, it's actually tailings. You know, the criteria, industrial criteria of processing of new ore sometimes are less feasible than to reprocess old mine tailings. So it's quite often that we have these consulting projects of that kind, and we have publications about that in our database. The next one is to contribute to better understanding of the pyrogenesis of the deposits through detailed studies of accessory minerals. Definitely, when you have the accessory mineralogy that keeps all the information on its own occurrence, their associations, it's always, I would say, the possibility to read through the genesis of the specific ore body, understanding its thermobarometry, everything to do with temperatures and pressures of the occurrence of different mineral phases. It's very important to understand, for example, the genesis of a specific ore body if it produces a certain amount of metal, so we understand its main factors of concentrating the valuable metals, right? So this is kind of a very important thing, not just for geoscientists, but also practical thing. For example, some rare metals that would lead to understanding of the pyrogenesis could lead to new deposit discoveries, because there are analogs of this kind of mineralogy somewhere else, so we can always track these between these two different areas and find out that new deposits can be there. The next one is conduct analysis of losses in tailings from concentration mills. This is very often consulting projects that the type of consulting project that we do. We usually have 3 different samples from the specific part of the flow chart, where we have the concentrate, or say product, we have tailings, and we have some intermediate products, right? So we can always find out by hydroseparation specifically, we can always find out why are the losses, in what form, what grain size, I mean, any even chemical process. There are also tailings from chemical process that we can, use EPD on to extract, residues of metals from scrap, for example, and then also concentrate them and understand what are the losses, why are they in the tailings. So now, before we start on practical things, I just want to mention once again that there is a special database of publications separated by different sections, like accessory minerals, like indicator mineralogy, and technical part of application of electric pulse and hydroseparation. And as I said, in the end of our course, we would want you guys, whoever would want to get the certificate of our company that proves that you guys being trained, I would want you to make an essay in one of these areas, whoever wants to choose which area, of application of electric pulse disaggregation and equipment, or different applications in mineralogy or mineral processing. You can go through and make an essay about anything you want, any section, and we will publish that, either if it'll be up to standard, we can make it a decent research publication. I can help you make it and publish it, and we definitely be able to publish it on our social media channel, such as LinkedIn, Facebook, or any other that we will choose. So thank you very much for this part of the theory on the stage 3 of our training and internship, and we switch to Oleg, to his lab. I want him to show you guys how to make wet-sieving, and I will comment basically how that should be done in a proper way, in a proper manner. So I hope you hear me still. So we can see 2 different fields of vision. The left one is wet-sieving part, and the right one is hydroseparation. These 2 we will have to discuss today. So Oleg will be doing wet-sieving, and his assistant Alexander will be using the camera to show you precisely how this should be done. So Alexander will hold the phone to show you guys all the different parts of wet-sieving process that Oleg will be doing. Oleg will now switch the camera of the phone, so we will see. Yeah, exactly. So down below on the right, you will see the field of vision that will show the part of wet-sieving. So you see guys using rubber gloves for wet-sieving. So manual approach, as I said, is more sensitive, more adequate. We use manual approach for this one because we work with very fine grained material here. You see those sulfides. And Alec is washing down sieve the amount of material after spark 10. Maybe we should hear from you guys, or it's talk right away. Okay, so Alec is washing down to the sieve. What is the sieve size, Alec, that you are using? So we need to know the grain size. What is the grain size you're using? So this is a Spark 10 product. How much? Alec needs to. Okay, so the sieve is -1 so it's 1, right? It's okay. So we go. First we process all the material of after Spark 10 using 1 mm sieve. So we have +1 and -1. That it has to be done the way that he does it. So basically, he pours pretty much everything in one sieve, 1 mm sieve. It's all done in a tray, plastic tray, so no spills and nothing get lost. So you can see he reunions the part of Spark 10 and Spark 2 all together because it's all this. And now he washes it through. As simple as that. Nothing special. Okay. Supposedly it's now being processed. And he rejects all +1 into a separate dish. So now we have -1 and +1 separate. So this amount is +1 mm. We don't work with it. We reject it from balance because that weight can be deducted from the weight of the sample. It's all the same sample. So we had primary weight of the sample that went to EPD. There is oversized +1 mm, and there is undersized -1 mm. So +1 mm can be weighed, dried weight, and deducted from the primary weight of the sample. So it haven't been used for hydroseparation. Now you can see the set of sieves. One sieve stays on another. So the lesser size is on the top, the coarser size, the finer size on the top, and coarser size at the bottom. So this set, it's absolutely clean after ultrasound cleaning for 1 day, as we discussed, and then monitored under binocular microscope if there are no particles stuck in between the grid. So it's very important to make sure that they are clean. So the sieve size on the top, this final one, the finest one, how big is this? Alrighty, now you can see everything. You can see from the side, you can see from the top. Anyway, so that's the sieve from above. So what Oleg does, he brings the whole tray up, I think. Yeah. And just pours the whole set with the same sample. It's a little bit of a delay, which is good in a way. So it's all -1 mm, goes now below 0.5 mm. The coarser sieve size is 0.5 mm, and everything is now being through 0.5, the whole amount of sample. So you can imagine that with automation, it won't be so accurate. This one's like you not spill even one drop. And now he does it by hand, manually, just grabbing the first sieve. It's very important to see like everything to make sure that you guys be able to do it on your own. Later on, you'll be our employees, I hope. because it will be 10 laboratories around the world. That's what we've planned for our business development. It will be 10 different laboratories, and definitely they will need staff. So you will be qualified. You will be getting our certificates that you went through training. So anybody would be interested to hire you in one of these 10 labs around the world, because you will be able to, yeah. So you can see easily. So he washes the sieve from below into the sieve that is underneath. You can use any water source, but we use the water from the tap. Here it is. So this is whole amount of plus 0.5 millimeters from the same sample. Okay, that's done. So we have a special place for the sieves. Sometimes you get much more sample, and you can see that immediately he makes a little tag for the specific size fraction, simply because to remember anything, there is a tag under each dish. So we use these wide mouth beakers, that dishes, that are very handy. They're wide enough to host enough material, and also it's very well organized in terms of space with his dishes. So you can see another sieve. He is going through another sieve. All that went through 0.5 millimeters went to the sieve below. He does the same with another sieve, same approach, rubbing it by hand and washing it in the sieve below. So that might be 250 microns. The sieve. If you can see that spills coming out of the sieve in the same tray, so we can always reconcile that part that is lost in the tray into the same, wide mouth dish. So these particles can get back, can go back to the same dish. See, whatever is spilled can be reunioned. That's it. This is how we reach ideal weight balance, because we don't spill, we do not lose a particle, which is not possible with automation. Slowly rubbing another size fraction through the sieve. Pretty much the same treatment all the time. But you can see that it's quick. Not a big amount of sample, but we just had that fraction to show you guys how is it done. Sometimes it has to be done several times for one sample, because here it was roughly, I don't know, maybe 200 grams. So for big amount of sample, you have to use the same approach several times, because it's definitely not enough room for the whole amount of sample if it's bigger than 200 grams. So you have to use the same approach several times through the same set of sieves. So that last sieve, minus 63 microns, it's the most cloggy. Like, it's not easy to clean like the previous ones, because it's very fine grain. And you can see that it's all set on the special plastic set of two different buckets. So they contain now all the material that is below 63 microns. So all these size fractions are now ready for hydroseparation. So that's the finest grain size, 63 microns. Most informative. Everything that's below 63 microns is most informative fraction. It has got all the accessory mineralogy. It has got all these platinum group minerals that we expect, together with sulfides in gabbro-norites from late Yokodo variant late intrusion. So we now have all the size fractions throughout the whole set. So that's the finest one in that bucket. It's a little bit more water than needed, so we tag it and place it for settling, for particle settling in this bucket, maybe overnight, maybe less than that, but we want all these particles to settle down, reject some water, and use it for further hydroseparation. So now the hydroseparation starts. On the amount of sample, we go from the coarser one, but this time we will show you hydroseparation on whatever grain size is ready for processing. Would you mind, guys, to explain what is the size fraction and everything, so people will understand what are you working with now? So we've done wet sieving. That is a treatment that you have to do before after pulse, each time for each sample, to separate, to basically separate between different fractions. And in an ideal world, as we say, we take an aliquot, dry these tailings, hydroseparation tailings, later take an aliquot for assays to make sure the concentrations between different size fractions also. So how the concentrations of valuable elements have been distributed throughout different sieve sizes. This is for reconciliation of chemical balance as well. So we know for sure that we can recalculate whenever we've got mineralogy, we can recalculate all minerals to chemistry and understand all the balances. It's very important. But this time, we show you how to fill the tube. So we place the glass funnel on top of the glass tube and pour the material through this funnel inside the glass tube. This is how the hydroseparation process is loaded by the grains, by the fraction, sorry. each time, it's not easy to see though. Guys, your camera is shaking a little bit. I mean, anyway, so this time is we are using short glass separation tube. There are two types of tubes. One is long and one is short. There is a computer, as we say, with special control panel there. There are different control panels, but this one is for using hydroseparation in a semi-automated mode. It's whenever you have an experienced user who can do it on his own knowledge, you know, how to use the hydroseparation device, which regime to use, and so on. So you can see that hydroseparation on the left upper frame, you can see that hydroseparation process has started, and you can see particles jumping up and down. Some particles are led upwards out of the GST from the top, and some particles stay at the bottom. So every situation is monitored under the binocular. You can see it on the top right corner, so that Alexander, the assistant, Oleg assistant, can monitor what particles are coming out of the tube by placing the white mouth beaker underneath. He can always see that, and they monitor what kind of particles is he getting rid of using hydroseparation to be sure that he's not losing particles. You can put it under the mic and see what are these particles. You will see now these particles. Here they are. So mostly silicates. They are ideally preserved, that you can see the crystalline shape. Anyway, so we're getting back to hydroseparator. We see that the separator works all right. In this short glass separation tube, the whole hydroseparation. At the bottom, you can see the mixing of different particles, and some particles go up and the others stays at the bottom. So those which stay at the bottom, they are heavier, and those, I would say, denser than those that are coming out of the tube. And so every time switching the dishes is possible to see what are you getting, what are these particles that are coming up out of the tube. You can always use the needle to make sure what are these minerals that are coming out as single particles, as single mineral grains that were recovered by EPD. Supposedly they all are single mineral grains or crystals. So it's very easy looking, very easy, right? But in a way, it's a high tech, because one had to use his knowledge to make this technology working. There were many people designing this technology, different physicists, different technologists, different engineers. So now it is fully operational for concentrating particles of different density. So you can see these particles. What are these? I think that Oleg will have to comment. I want Oleg to comment what he actually finds in the tailings, hydroseparation tailings. Maybe he can comment. Oleg? Oleg is doing a little bit of rearrangement of the frames. Which So which fraction is it? But what is it, the fraction? Minus what, 150 microns, right? Right. So these are associated, the sulfides are associated, so it's not recovered completely, you mean, on the coarser size. So do we see separate pyrite and other sulfide grades there in this fraction? Can we check? Yeah, that's the final concentrate, right? This is the final concentrate, or is it the reject of the tailings? What is it? Okay, preliminary concentrate. Okay, all right. So guys, you have to understand that hydroseparation is done stages. So we usually start from long GST, long glass separation tube, to get, I would say, up to 50 times concentration of the primary sample, of the primary fraction. Then we switch to small GST as GST and produce preliminary concentrate. That is preliminary concentrate. You can see it's still large amount of the concentrate, and you can always reunion one preliminary with another. So since it's done in stages, you can get to the very final product at some stage in the very end, which is 5 to 20 milligrams, and that's the one that will have all your sulfides, those nicely recovered sulfides. We can see now that already at minus 300 microns, there is a recovery of sulfides, though they are still intergrown with other rock-forming minerals, so they are not ideally recovered sulfides. They're still within the intergrowth with other rock-forming silicates. To ideally separate particles by density, they have to be ideally recovered, and there shouldn't be any attachment to other minerals. We can't see anything. It's better be a digital camera. It's better be digital. Тебя слышно? Слышно. Okay, there is a large sulfide grain there in the concentrate. It's preliminary concentrate still because it's, you see, quite massive amount of grains here. We can always clean it more and make it just sulfide concentrate. It's just that we want to be quick and show you guys how the separation is handled. So you can see even in this case with 0.1 ppm sulfide content, we are capable to find separate sulfides in a very dense, very hard rock that otherwise we wouldn't be able to separate if we're not using EPD and HS. So Oleg is now showing large sulfide grain. What is it? Where is it? I can't see it well. Can you enlarge it somehow to show us under the mic? Oleg? Unfortunately, Oleg doesn't hear us, I think. Or there is a delay, I don't know. Can you clean it a little bit so we can see that it's a separate sulfide? So Oleg will now take a needle and show you guys the sulfide grain. I mean, we are talking about number of sulfide grains that we need for further research, and I think we can have, thousands of grains concentrate. So you can imagine if in the preliminary concentrate we are getting these coarse sulfide grains, it can be that the finest grains size will have many more, because you see the coarser, the less probable. The finer, the bigger amount. Yes, we can see that. It's for the first time that I think that no one else is. What is it, Alec? So Alexander is still doing hydroseparation while Oleg hand picking, I would say. Yes, that's the pyrite, right? What is it? Yeah, there are few sulfides there, you can see. Just pyrite, that's just pyrite. But you can see the outlook. You can see how crystalline are these. They are ideally preserved. Nice particles of pyrite. You have seen that sample. There is no way that you can recover these pyrite crystals any other way, because it's electric pulse which allowed to extract it in as pristine crystal of pyrite. So that's magic that happened. We have had that 1 kilogram sample. We've processed through EPD, 2 types of EPD. This one definitely has recovered on EPD's part 2 stage. There's large pyrite particles. So we didn't expect this to be so coarse, minus 300 microns plus, I guess, 125. So they're quite coarse. So we expect many more sulfides, not just pyrite, but many more others. Definitely, this will be a very good result that we'll then be able to evaluate, and the client will be happy because he could do any process, mineral processing on these samples because of this density and hardness of and compactness and fine grainedness. So you can see these crystals, these particles are all separate grains, separate minerals, which is very good. There are some intergrowth as well, but that is a coarse fraction. Just wait and see what we'll be getting from the fine grain fraction. So, guys, would you like to show anything else, like specifically hydroseparation, or let's ask our audience, okay? Maybe they would want to see more of the hydroseparation. Maybe they would want to see more of the results of hydroseparation concentrates. I will ask them using our Telegram group right now. So tell me, guys, how are you there on Telegram? I'm watching the Telegram right now. What you want to see more of the hydroseparation? Like to see more products, and basically, do you understand the whole concept? Urja, Eva, others, whoever is more active. What would you want to see more, like the process of hydroseparation, or maybe hand picking? Guys are writing something. Let's see. Okay. Guys would want to have more of picking because they say, well, I would say guys in the lab, they want to make more hand picking because it is a little bit late now, so they will be showing the hand picking. Because hydroseparation takes a little bit more time because we have to load and reload and make those concentrates. But the concept is clear now for guys. So if you want to show them a little bit more of hydroseparation, Alec, no problem. You can show more hydroseparation. Or if you want to make hand picking also, it's for you to decide. And Urja is asking, how can you determine which fraction will have desire? Well, out of the experience, anything that is rare recovers at the very fine grained fraction. Okay, so it's very seldom that you can see coarse grains of the accessory recovery. Okay, it's usually in the very fine grain. Definitely, if we find something in a coarse grain, like if we found sulfides in coarse grain, it should be many more in the finer grain size fraction. It's like with very rare platinum group minerals, they all recover minus 300 microns. You can rarely see larger grains. It's mostly for these late intrusions, it's basic and ultra basic kind of mineralogy. It's always recovery on a very fine grain. Eva is asking, when determines when we change the larger glass pipe to smaller in HS? Okay. The tube is long simply because it hosts more material. So, because you need more space to separate particles from each other by density, you need more space. So the longer tube is used for bigger amount of sample, because whenever you start with the fraction as a raw, you have maximum amount of material. You have to cut the size of that amount. So you need to fit as much material as possible into the tube, and you are not so cautious about the sensitivity level, say. You have to cut the amount, right? It still be the same representative balance of minerals, but then you have to cut the size. So the distributions of heavies and lights will be the same, but the amount will be smaller. So whenever you have a subsequent amount of fraction that can fit in small GST after certain amounts of sessions with long GST, then you can switch from long GST to the short GST, and so it will be just enough amount of space for that amount of preliminary concentrate to feed the shorter glass separation tube. As easy as that. But the first stage, whenever you make with long glass separation tube the concentrate, is really the cutting the size or amount of the specific fraction. And that is less sensitive than the next stage on the shorter tube, where you separate very, very precisely by physical density. You can see that any student can work with this technology, not like with EPD, though EPD Spark 10 is used, and it's very safe. So with hydroseparation, it's even less headache. It's just that you have to be very accurate. Do not spill particles on the table. Even though you spilled it in your tray, you can always reconcile it with the portion for HS. So wet sieving was simple, I hope. You understood that there is a set of sieves that starts from the coarser below down to the finer. The range of size fractions starting from minus 0.5 millimeter down to 63. It's just those sieves that are standard, so any columnar sieves can be bought with this certain size ranges, but they can be different. They can be measured by mesh size, they can be measured by microns, but they are standard. So whenever you have the column, you can use the same approach. Putting it the sieve size on the bucket and just sieve it through using the water and your hands manually. You can also use automated sieving, which is more expensive in terms of capital. Eva is asking, can HS be applied to soil samples as well? Definitely, if you get rid of organics. So usually the soils get burned, specifically, I would say, producing the ash from organics. And then through the set of sieves, and then yet again through hydroseparation. Definitely, yes, the soil has been used widely. I'm not sure, though, if we have publications in Mineralogy Online for soil. Yes, I know about soil mineralogy and soil chemistry for heavy metals, for example. We have worked on even the residues of the filters from air conditioning filters, you know. So people would want to know the concentration of heavy elements in the air, right? So there is a special filter that captures those heavy particles. Then these filters get burned, and then we make it through hydroseparation and get those heavy particles that are sometimes between a few microns to 100 microns. And then the whole heavy elements as separate particles can be understood. What are these pollutants? So the soil is the same for pollution, can be understood. So one of the applications of highly sensitive hydroseparation method. Yet again, guys, feed the glass GST using the glass funnel. So we have about 2/3 of the GST filled with the fraction. We need a little bit of space for the amount of material, some amount of material to spread through nicely through the glass separation tubes through the whole length. So to make sure we have separation process, some particles stream down, another go up. So you can see how's it working. Here is some material under mic. It's -1 + 0.5 millimeters. Here is glass separation tube. The separation on the left haven't started yet. It's just fed into the GST, and you can see this is long GST this time. So the separation has started on the right image below. You can see the fraction is streaming up. This is the very accurate process. So you can see that the water flow is regulated by a needle valve. So we have that process of laminar flow through the use of special needle valve, and then we use specific regimes of hydroseparator, which is impulse process. We can see that the process has started. These pulses are now being transported to the tube from the water pump, specific water pump, which is hydroseparator, water flow regulator, we call it WFR. And so you can see that particles are started to come down from the GST onto the white dish. Each time this dish is monitored under the mic. There is a question. So we have a questions. The next from Eva: do the restrained all the sieves pass through HS, or just the grains that pass through the thinnest sieve? No, every grain size will be used for hydroseparation, because we need to see the picture throughout all these size fractions, because the sample has been separated in different fractions simply because otherwise it won't be possible to separate them by density. We stay off the size of, so we try and make density separation as accurate as possible. Within the different size range, it's possible to use density, physical density, as the factor of separation, right? So here is why we work with different size range. And the narrower the distance between different grain sizes, the better separation you would have. That's why we have those different 5 size fractions. So you can see that guys are switching the dishes under the glass GST, so they can always monitor what is coming out of the GST, what are the particles. And they can put it under the mic and see whether the minerals are changing, you see. So sometimes if they are not changing, there should be the switch of the regime, because you need to really change the assemblage of minerals so that you can see basically the density is different for different minerals. Or otherwise, the balance is. And so there are regimes that can be worked out for a specific sample, and then loading and reloading from GST, and just repeat all the same regimes. So the first portion, I would say, of the sample would be the one to understand which is the best regime for processing of the sample, and how can we use automated approach to process all the residual amount of sample. So now it is just used for understanding the best regime, and later, once regime is set up, you can always use all the same rating, the balance of the sample, the balance of the fraction. So you can see that there are two regimes. One is mixing regime, is a separation. They just use two regimes right now. So I'm here with you guys. So we now have 1, 2, 3, 1, 2, 3, 4, 5 different frames, right? One, two, three, four, 1, 2, 3, 4, 5 frames. One is что сейчас надо сделать? Excuse me, guys, we have to speak Russian a little bit. Ты говоришь. Okay, there is a question. What is the use of grains? There is a question. What is the use of grains? The grains that remain inside the glass Eva. You see, there is nothing remains. You haven't seen that we actually reject all the concentrate that is, that stays at the bottom. Can you, Alek, can you show how to basically how to evacuate the concentrate from the GST? People would want to see that. You just have to wait a little bit till we get to that point when the final concentrate will just stay in the separation tube, and then they will reject that amount of concentrate to the separate dish, and then you will see this final product. They're just switching one and the other dishes. It's all the same product. They are doing it for the first time. That's why they just monitor every amount of sample fraction that is going out of the tube to make sure that they are not losing any sulfide grain. They are not losing it. Then they reunion that material together because it's all the same material. It's all tailings, and they are trying to reach the point when there won't be any separation at the bottom of the tube. They will show you now the bottom of the tube, so you will see what's going on at the bottom. Can you guys show the separation process? Here you are. Somehow it's not visible. Not easy to see, I don't know why. Alec, can you show us the bottom of the with the camera? Is there the phone camera that you can use? Here you are, Alexander is trying to show, but it doesn't work. The framework doesn't work. It's black. Still black. Nothing shows up, Alec. We can't see anything on that camera. Okay. We are waiting till this camera will work. So hydroseparation is done in stages. So the first stage, preliminary concentrate with long glass separation tube. All the less heavier particles come out of the tube from the top, and the heavier particle stays within the tube at the bottom. I just wanted to show you this separation process by itself. There are videos that you can see, but we want you guys to see physically on your own eyes how is it done with this sample that we've chosen for the tests. We have already found the pyrite grain in the coarse grain fraction in the preliminary concentrate, which proves that we have recovered sulfides throughout the whole range of grain sizes. And the only way to separate these sulfides would be to use hydroseparation. But yeah, we should see it in a moment. I don't know why we can't see it. Alec is trying to fix the problem with his camera on his, while Alexander is showing that, trying to use this. Yeah, here you are. So now we can see that's the separation. You see that the GST clean, it was dark, now it's grayish. And you can see that things are settling down at the bottom. Once again, camera doesn't work. It's like switching on and off, Oleg. It is switching on and off. May not be, you know, internet or something. Anyway, guys, can you show us how to reject concentrate from the tube? We can just see if there is any enrichment in the final concentrate. If you don't mind, we just want to reject that residue, that heavy part of the fraction that you've loaded onto a separate dish and put it under the mic, because I think it's just the time to do that, as far as I can see. Can you reload? Alec, do you hear us? It's okay. Can you just reload the amount of material from GST and show the concentrate? And guys want to see how do you reload from the tube. So we switch the dish. Each time we change the regime, we also, because any regime, whenever we switch to the other, the separation process is changing. So then you can program the device and it does it automatically. But before you really know how much time do you need regime, you have to make sure that it's working and you are not losing the grains of interest. Hello, guys. Can you actually reject the concentrate from the tube? Is it ready already? Yeah, you can see that the final the preliminary, I would say, in this case, because it's still a lot of material at the bottom, but that amount of material can be reloaded from the glass separation tube onto the separate dish. And I think that, Alec, your camera wouldn't work, so do not waste your time on this. So you can see that the trays, one bigger tray and another one inside the bigger tray. Again, the portions not to lose a grain for any reason, by spilling, by changing vessels. It's all collected eventually in one vessel. So any grain can be collected and not lost. So that's why we have such a minimal weight loss of the final product. And it is very interesting process as well. Guys like to use this process because it's really, like playing with sand and water. And always monitor grains under the mic. It's more or less like miracle when you that you cannot see in the primary fraction, and then they appear in the very final concentrate. So that's tailings from the same amount of fraction, you can see. And now I hope that they will reload preliminary concentrate from show it. They do it. Can you show the reloading process? Is it already the time to reload? Yes. No. Yeah, it takes a little bit of time to process some amount of material. Okay, now he is reloading. Alexander is reloading the amount of material that's left at the bottom of the glass separation tube into the separate dish. You can see how is it done. Can we see the reloading? We don't want to see the, yeah, here it is. You see, that's the concentrate, preliminary concentrate. Definitely it should be much smaller. As we just said, it's 5 to 20 milligrams. This one is much bigger. But yet again, just want to say that have enough to get to the final concentrate. It takes a little bit more time. This time, we don't have that amount of time here at this stage of training. But at least we're going to be showing you the final product. of hydroseparation. It's definitely important to preserve all the sulfide grains in it. Let's see. Alexander is loading more fraction to the GST. As you can see, this process is in the batch. Guys, we don't have time for this training. Can you actually show us the preliminary concentrate to make sure that we've resulted some of the sulfides already in this first batch? Because we don't want to see the whole fraction to be processed simply due to no time. But you can see, guys, that he's feeding more fraction into the GST for another batch. But I hope that Alek will have now more attention to the product, because we have shown already the hydroseparation process. Yes, Oleg is doing some microscopic observation of the final product. Let's see what is there. Yeah, there are separate particles. Hopefully that he will be able some sulfides there. Yeah, that's important to see that we, after tailings has been received, these tailings are put into the oven so that they dry out, roughly 70 degrees. They dry out, and you can always, and then you can treat them dry for hand picking. So he will show you the hand picking. I guess the dishes are very hot. So he will be doing some hand picking on previous amount of concentrate. He will be picking sulfides for you guys. And we'll show you the nice crystalline of, I think, pyrite. We will release images of in the course of our training, so you will be able to see that. So this is the hand picking process. Usually it's done by needle and a little bit of fat, you know. So you touch your face usually by the tip of the needle. That becomes gluey with the fat from your skin, and it's easy to capture grains by that needle from then on, and transport it from one dish to the other. But he will just be showing you, I think, he will make a circle around specific grain to show you guys that this is sulfide. You can hardly see it. Alek, is there a way to see it under the camera? So he found the sulfide grain that he wants to show you, I guess. Let's see what he's got there. You can see that all these grades are different color, different shape. That shows ideal liberation of different types of minerals and their intergrowths. They're very nicely distributed because it's all the same fraction. Unfortunately, it's not easy to show separate grains that way because of the quality of the image of Twitch. But you can see different colors for sure. So these grains have different colors. That means that these are different grains, separate minerals. You remember that piece of rock that it was before? Definitely didn't look really like crystals. This looked as if this is monomineral substance, very compact. Here you can see that it was all composed of different types of mineralogy. And you see they are very small, though they are coarse-grained enough, but they are very small. They are easily attachable to because of their statics. Let's wait until Oleg will make the nice view of the grain, of the sulfide grain. I think that'll be it. Alexander, bye-bye. Yeah, it's time now to go home, right? It's already 8:15. So these guys have to go home. So, Oleg, do we finish today? We haven't been able to see much of for the moment. Eva is asking, can we put the final product into XRF and see the elements in order to have an idea what to expect? Yes, you can. And definitely we do the following. We have the tailings of each fraction after hydroseparation. Whenever we've extracted certain amount of grains that we needed for other types of in situ or grain analysis, whatever we need from the concentrate. The residue is tailings, and these tailings can be analyzed whichever method you want to use, whether it's assay, wet chemistry, anything, it's enough material for that, or X-ray diffraction, or X-ray fluorescence, but then X-ray diffraction is popular in this case. So definitely you can use this, or electron probe microanalysis like EPMA. Usually it's this one because you have separate grains, and it's not needed to make to use chemistry in this case. You can usually use single grain level to understand the chemistry of different minerals, because we are going down to mineral time. We are not having the sample already. You can use the sample for the primary chemical assay, and that will have all these elements that you need. But if you go fraction by fraction, you have to go down to a single grain analysis, so that you will be able to reconcile that chemistry that you have from primary sample on the phase level, on the mineralogy, to understand the distribution of these elements throughout different minerals. That's the main important application of this approach. Unfortunately, the quality of the Twitch stream is not good enough to show you guys the individual grains, and maybe our cameras are not as good as they should be to make them usable for this purpose. But this is just a good way to show you how simple it is to use our equipment, use our methods, going down to a single grain and try and implement different types of mineral analysis. This time is optical microscopy. Next time it will be something else. Like whenever we have polished sections prepared, we can use monolayer polished sections for understanding different parameters of mineralogy, such as grain size and analysis on the face level of each grain. So I should call it an end of this stage of training. Thank you very much for being with us. In the end, because he wants to show us something. Let's wait a little bit. Maybe he wants to show us any type of sulfide that is not pyrite. Maybe pyrrhotite. Oleg, what do you want to show us? Oleg? Pyrite, pyrrhotite, and pentlandite. So 2 to 3 different sulfide minerals in the same preliminary concentrate. It's not bad. Supposedly that there is no any other method to recover grains of these sulfides from this gabbro-norite. We've done pretty well. So this is just the coarse grain fraction. Whenever we'll be doing final size fraction, that will be many more grains, and actually the final concentrates will all be just sulfide concentrates. So far we haven't had enough time to make it and show it to you, but later on the next stage, on the next webinar, you will see very nice concentrates that then be made into separate products for research, like monolayer polish sections. I have to call it an end of our stage for internship and training. You guys take care. Thank you very much for being with us. Oleg, thank you so much. And Alexander, thank you guys. You've done well. Take care. Thank you so much, Oleg. Okay. Thank you so much for being with us. Thank you for watching. It was very nice being with you and answer your questions. Thank you, Eva. Thank you, Urja. Thank you, Chetan. Thank you, everybody who was with us. And next time, see you tomorrow.